Hello, I am Dr. A.J. Kumar. Let me go grab my Artin book. My cat's here, so she might make her presence known. My sweetheart. Okay, I got the physical book. This one looks really simple. This next section, I haven't looked at it thoroughly, but I think it's just Cartesian product. So we start on page 64. Alright, which is just product groups. And then quotient groups is where he concludes the section, and that's kind of the heart of the matter. I think that's really the heart of group theory, is the idea of quotienting. It's heart of mathematics in a way, which is why group theory is so central. Anyway, okay, and so, and the notes from last time, I tried to upload them to my locals, and it literally took down my whole locals board. Okay, and I'm also going to do a new thing where after I finish reading, yeah, it's going to have a 500. Literally takes down my locals board. I mean, so you wonder why I'm working on OPHTTPD and Marketplace. This is why. So because I am just sick of using all of these services with locals, Minds, Gab, Twitter, YouTube. Those are really the core ones I use. Subscribestar, BitChute, Odyssey, and I have a whole list of them. And it's just, if I want to start blogging Substack, and you need Gumroad. It's just, I'm so sick of all of these fucking services, none of which I can control. Right, 500. Any one of which could cancel me at any time, and I really have no way to do anything about that. I am just sick of it. I'm going to write all of them myself. They're all going to fit together nicely, all under one thing. It's going to be decentralized. Anyone can use it. And then there will be a centralized service which does things like search, algorithmic recommendations, the sort of social networking aspect of it. That has to be centralized. There's no way around that. Or there's stupid ways around that, and they all suck. But part of it needs to be centralized. And then there's also going to be a decentralized media storage system called OPSS, which I've written about quite a bit. I wrote a post on Sanger's forum about that. So anyway, this looks pretty simple. So we're going to read this. It doesn't look very complicated. I didn't look thoroughly. I'm going to read this, and then I'm going to make the thumbnail in the video, and that'll be a good exercise, because what it will be is me going through and having to try to figure out a way to represent the subject of the book, or subject of the section, in a single image, and to kind of make it artistic. Okay, so we're going to go through and highlight terms just so that we get a sense of what is talked about. And then if I see a term that I don't know, I will maybe mark that in a different... No, I'm not going to go crazy with my colors. Product projections. Okay, so far this is exactly what I expect. Okay, nope. That looks like it. Then we're going to go in blue, and we'll highlight any references. I'm just scanning. I'm sure I'm missing some, but I don't see. So it's pretty dense. $211D, okay, but that's just like the previous page. Doesn't really, 265. It's a previous reference. Okay, I think that's pretty much it. 265 is the only one that's really worth looking up. 265. Let's see. There's obviously a link to buy the book down below. Please go buy the book. I'm assuming you bought the book and that you're reading along with me. 265, this is on page 52, and this is, you know, you're studying along with me. Okay, and this says AB equals BA precisely when AB A inverse is equal to B. Right, okay. Oh, so, God damn it. Okay, and this way you can kind of see, but also maybe this way you kind of can't see, and that'll help me if I have copyright issues. I'm assuming again that you bought the book and that you're reading along with me and that I'm helping you in that regard, but I'm not. This is not a substitute, meant to be a substitute for the book itself. Okay, so let G and G prime be two groups. The product set G times G prime, the set of pair, right? Cartesian product. This is very standard. Yep. Sure, injection and projection homomorphisms, very, very standard. God damn it. Anyway, it's obviously desirable to decompose a given group G as a product that is defined. Right. So it's saying it's obviously desirable to decompose a given group G as a product, that is to find groups H and H prime such that G is isomorphic to H times H prime. The groups H and H prime will be simpler, and the relation between H times H prime and its factors is easily understood. It is rare that a group is a product, but it does happen occasionally. For example, it is rather surprising that a cyclic group of order 6 can be decomposed. The cyclic group of order 6 is isomorphic to the product C2 times C3 of cyclic groups of order 2 and 3. To see this, say that C2 is equal to Y and C3 is equal to Z, with Y squared equals 1 and Z cubed is equal to 1, and let X denote the element YZ of the product group C2 times Z3. The smallest positive integer k such that x to the k equals yk zk is the identity 1, 1 is k equals 6, which is the LCM. So x has order 6, so x is equal to yz, okay. C2 times C3 also has order 6, so it is equal to the cyclic group X. The powers of X in order are 1, 1 yz, 1z squared, y1, 1z, y. So I'm wondering if you take z mod 6, so take z mod 6z. This should decompose into z mod 2z times z mod 3z. So, and then a generator for this is 1. Okay. So 0, and I'm going to, instead of 1, use E. E, 1 is analogous to y, z, which I guess would be Okay, yeah, I'm doing additive groups, so 0, 0. That'll be better. 0, 0. 1 is analogous to 1, 1. 2 is analogous to because now I see. Okay, let's just keep going. 0. Yes, what we want to do is pick a generator. Okay, and there's only one generator. So what I'm thinking is if you take the multiplicative group instead. So you look at the z mod 6z with respect to multiplication. Is that a field? No, it isn't. Never mind. Forget what I said. This will be 0, and then z squared would be 2. 3 has the relationship 1, 0. 4 is related to 0 and 1. And then finally 5 is related to 1 and 2. So maybe let's try plotting this out. So if we plot this out in green, go from here to here to here, down to here, here, then back to here. This just looks random. 4. It's like a shoelace, so it goes up, up, and back down. Okay, so there is a pattern. Draw it out on your own and you'll be able to see what the pattern is. So do what I just did. Draw it on a piece of paper carefully, on a piece of graph paper carefully, and the pattern is kind of obvious. That's an interesting pattern. Huh. So yeah, this is what I was going to ask. Is this point, is this true? And it looks like it is. And I'll highlight it in pink. It says there is an analogous statement for a cyclic group of order Rs whenever the two integers R and S have no common factor. Because that's kind of what the logic seems like is going on here. Anyway, let R, and we get even more information. Okay, so there is more to this. Okay. So let R and S be relatively prime integers. A cyclic group of order Rs is isomorphic to the product of a cyclic group of order R and a cyclic group of order S. Let me zoom in a little bit. On the other hand, a cyclic group of order 4 is not isomorphic to a cyclic group of order 2. Every element of C... Okay. Be relatively prime integers. That's important. Okay, and I don't think he proves this, which is a glowy move. But this relatively prime part is important. Is not isomorphic because 2 and 2 obviously have a common factor. Every element of this has an order of 1 or 2, whereas a cyclic group of order 4 contains 2 elements of order 4. This is a really powerful theorem. I wish I could see a proof right away, but it doesn't. It's not obvious to me how that would work. We're going to do a much deeper dive when we go into dominant foot, and then what I want to do is kind of circle back. How do you make this computable? How do you pull back this theory as much as you can and make it computable and applicable. Shut the fuck up. Anyway, the next proposition describes product groups. 2.11.4. Let H and K be subgroups of a group G, and let F from H times K to G be the multiplication map, right, defined by F of HK is equal to HK. Its image is the set HK. Oh boy, I remember this with dominant foot. Oh god. I remember sweating over this theorem for a very long time when I tried to read dominant foot. Right. F is injective if and only if the intersection is 1. Okay? F is a homomorphism from the product group H times K to G if and only if elements of K commute with elements of H. Weird. Okay. Whoa. If H is a normal subgroup of G, then HK is a subgroup of G. F is an isomorphism from the product group H times K to G, if and only if the intersection of H and K is... Oh god, this is going to be a difficult theorem, isn't it? Oh god. I was deceived by the length, but this is a lot of... Okay. If F is an isomorphism from the product group H times K to G, if and only if H intersect K is 1. HK is equal to G, and also H and K are normal subgroups of G. Okay, well, we'll see. I'm going to need to read through this launch. Okay, so what page are we on? Printed page 66. Okay. So I'm going to need... I can't even read my handwritten notes. I wrote novel? Is that what I wrote? Mirror? There's no way to tell what I wrote. And then I wrote, there's a lot of hmms. Okay. So it is important to note that the multiplication map may be bijective, though it isn't a group homomorphism. When G is equal... Okay. I'm going to need to do a lot of exercises on this section. I'm going to probably need to do all of the 2.11 exercises. He has the exercises nicely split into sections. I have them all highlighted in my printed copy as do these. Okay. I'm going to need to do all of those. Those, I guess, will not be on my locals because I took my locals board down by accident. And I'm not going to even email them to get it back up because, you know, fuck them. I'm going to build a replacement and say, well, my local board was down. How's that my fault? If I just could have sent you an email, but it was easier to just build my own. The smartest mathematician who ever lived. Okay, so the first one, we're trying to prove this map, which is not necessarily a homomorphism, is injective precisely when the two groups are pretty much almost disjoint. Okay. So it's going to be suppose otherwise, prove that there's a collision. Okay. If H intersect K contains an element X which is not 1, then it also contains the inverse. And F of X inverse X is equal to 1. Okay, right, so F is not a duh. Suppose that the intersection is 1. Well, that's a sufficient proof, isn't it? Oh, if and only if. So it says, right, so we just proved suppose H intersect K is not equal to 1, then F is not injective. So F is injective implies the intersection is 1. Now let's suppose the intersection is 1. There's nothing she wants. She's just screaming just to scream. Like, she's got food, she's not hungry, she's just trying to make me miserable. Come here. Can you be a quiet kitty? Nope. Okay, I'm going to pause the video and go double check and make sure this cat doesn't want some food. Because I put her in my lap, and first thing she does is jump off my lap and jump towards the door, so I think maybe she's hungry. Good kitty. Alright, 1 second, I'm going to pause the video. Is there a way to pause the recording so it keeps recording to the same file? That'd be nice. Alright, let me make sure I have the mic on. Yeah, okay. So I'm recording again what happened. Anyway, it turned out my cat actually was hungry. Or at least feeding her made her go away. Yeah, poor thing. She's a sweet lady. Love that cat. Anyway, love that kitty. Best kitty in the world. Alright, so let's read the proof of this is maybe not the best time to read this section, but oh well. Let H and K be subgroups of a group. This seems like the main theorem. Let H and K be subgroups of a group G, and let A... okay, right. Right, so we're proving that given that H and K only have a single common element, which any two subgroups are going to have at least the unit element in common. Okay, we're supposing they are... Okay, let's suppose there is a collision. We proved that so we suppose that there is a collision, and we prove that the collision is on a common element. Okay. Okay, so we suppose that H intersect K is 1, and we suppose that we have two elements, H1K1 and H2K2, be such that H1K1 is equal to H2K2. Multiply both sides by H1 inverse, and on the right by K2 inverse, obtaining, right, K1, K2 inverse, you just rearrange that equation, is equal to H1 inverse H2. The left side is an element of K, and the right side is an element of H. Since H intersect K is equal to 1, they're both equal to 1, so K1 is equal to K2, H1 is equal, right. So H1K1 is equal to H2K2, correct, okay. B, so what are we trying to prove here? F is a homomorphism if and only if they commute. This was the part that surprised me. Okay. Let H1K1 and H2K2 be elements of the product group H times K. Did I set the bottom text to be correct? That's going to annoy me if I forgot to do that. No, it looks great. Be elements of the product group. The product of these elements in the product group is H1, H2, H2K2, and Oh, product in the product group. Yeah, I wrote down that confused me. Okay. I was just checking my notes in the real version. I read this like years ago. And f of that is that. Okay. That's the proof of that whole thing, is like 2 sentences? Okay. This is a really simple deduction then. Okay. So let them be elements of the product group. So the key fact about homomorphisms is that phi of fg has to be phi of f times phi of, or phi of xy has to be phi of x times phi of y. Okay, so what we're doing is we're taking the product in, so we're doing, here, let me do this. Homomorphism from h times k, so let's call this a, into g, okay? So we have h1, okay, and then so the condition for a homomorphism is that right, let's draw out the tree. So we have x and y. How should I draw this? X and y, and we combine them using multiplication in A. Okay, and x and y are in h times k. Okay, multiplication in A to get xy and then this would be phi of x, obviously feed through phi, and this is phi to get phi of y, and you combine these two, get phi of x. Here we go. This will give us phi to get phi of x, y. This is phi of x, phi of y, and these two have to equal each other. That's what this is the homomorphism condition, is this graph. Okay? So this would be h1, h2, or the product, so okay, so the product in the product group. So x, y, so let me maybe do this. X is analogous to h1, k1, and then y is analogous to h2, k2, okay, and then xy is analogous to h1, h2, comma, k1, k2, okay, and then phi of x times phi of y, or this is analogous to f of he starts with, this is phi of xy. This is analogous to f of h1, h2, k1, k2, which is equal to H1, H2, K1, K2. Okay. And then, right, and then F, okay, and then phi of X times phi of Y, this is analogous to F of H1. K1 times F of H2. K2, which is equal to H1, K1, H2, K2. Okay, and these elements are equal precisely when so let's set H1, H2, K1, K2 is equal to H1, K1, H2, K. Yeah, I see this mess of subscripts and my brain just melts. Okay, but we can cancel a K2 and we can cancel an H1. And then we get H2, K1 is equal to K1, H2, and this holds for an arbitrary H2 in K1. Okay, let's zoom out and look at the argument again. Okay, so F is a homomorphism from the product group H times K to G if and only if elements of K commute with elements of G. Okay, so right, so we reduce the it is a homomorphism to this equals this. Okay, and then that condition is equivalent to an arbitrary element of H commutes with an arbitrary element of K. Okay, and so that's just a very direct argument. Okay. That's a surprisingly direct argument for such a non-intuitive result, but okay. Or such something that I would not expect right off the bat. Anyway, let's suppose that H is a normal subgroup. Okay, what are we trying to prove? So if H is a normal subgroup of G, then HK is a subgroup of G. Okay. So H is a normal subgroup means that when we have G act on it, we get the same, it rearranges the deck chairs, but we get GH is equal to HG as cosets. Okay. We also note that KH is a union of the left okay. If H is a normal subgroup of G, then HK is a subgroup of G. Okay. Suppose that H is a normal subgroup, then KH is equal to HK, so that they're going to be equal. Okay. And that's what he's trying to show. Yes, okay, that's what he shows. Okay, closure of HK under multiplication. HK, H. Fuck this fucking glowy retard notation. I mean, look at this stuff. That isn't an argument. Okay, so H times K is equal to K times H. I agree. Closure of HK under multiplication follows. Okay, because we take an arbitrary H times an arbitrary K times an arbitrary H times an arbitrary K. Okay, let's dissect what this means. So we take in. So H is a normal subgroup of G, which means that in particular, if we have K1 times an H, this is, okay, given for all K1, for all KH in K times H, K, there exist H, K prime, H prime in K times H, such that K times H is equal to H prime times K prime. That's equivalent to the normality condition. Okay, so closure of HK under multiplication follows, because let's take K, little k, times H times X times Y, okay? So X is in K and Y is in H. I should color code these, but I'm not going to because I don't feel like it. Should I color code them? I should. It's going to be a lot easier to reason through this. Okay. So let's do K. So we have K times H times X times Y. That is a lot easier already. Okay. And we want to prove that this is in, that we can reduce this to a yellow, we have a yellow times a blue times a yellow times a blue, and we want to use the fact that K times H, so K times H is equal to H prime K prime. We want to be able to reduce this, the fact that for every yellow and blue, we can rewrite that as a blue times a yellow. It doesn't have to be the same blue and yellow, but every yellow and blue is the same, is a blue times a yellow. That's a much better way to think about the normality condition, I think. Is that given a yellow and a blue, you can rewrite it as a blue times a yellow. Thinking about things in terms of colors is a lot easier. And okay, but in particular, this H times X, we can rewrite this as, we can rewrite this as K, this blue times the yellow, this can be X prime times H prime times Y, group these two together, Okay, we're done. Okay. So closure, we have that. There's a really helpful theorem, which is if you want to prove that something is a subgroup, the subgroup criterion, that for all X and Y in H, you're trying to prove that H is a you're trying to prove that H is a subgroup of G. I really like dominant foot. We're going to go read that after we finish 212, and then we're going to do a bunch of exercises, which I don't know. Where am I going to put those? Because I don't want to solve the exercises and put those up in public. That's a breach of mathematical decorum to do that, to solve someone else's exercises in public. So I don't know where I'm going to put those videos. I guess I got to write OPSS, make them private on YouTube or something like that. I don't know. Or maybe just don't publish them. I don't know. But took down my locals board, I guess. Anyway, this is true if and only if for H is a subgroup of G. Let me write this. H is a subgroup of G if and only if for all X, Y, and H, X, Y inverse is in H. That's a really nice criterion that dominant foot uses a lot. Anyway, and it implies both of these criteria. Yeah, okay. So this, I like, let's save this as AA32. Anyway, HK inverse, right, okay. this proves closure of HK under inverses. Okay? So if H is a normal subgroup of G, okay, so let's do checks on what we've proved so far. So, yeah, we agree. Yes, yes. So F is an isomorphism. Oh. Okay. Suppose F, okay, F is an isomorphism from the product group H times K to G if and only if all three of the conditions above are true. Okay. So suppose that all three of A, B, and C are given. Okay. Then F is both injective and surjective. Why is that correct? It's surjective because H times K, right, is a subgroup of G, or is equal to G, so that's why it's surjective. Okay. It's not all three, it's, this is, okay, so HK is equal to G. Okay, so, according to, okay, so F is both injective because of this, right, this gives injective, this gives surjective, okay. So it's both injective and surjective, so it's bijective. Okay. According to B, it is an isomorphism. So isomorphism is always a bijective homomorphism, so we now only need to prove that it's a homomorphism. We need to prove if and only if the elements commute. So to prove that something commutes, you prove that I guess he's going to prove the commutator is equal to 1. Okay. So H times KH, HK, H inverse, K inverse is equal to H times KH inverse, K inverse. Since K is normal, the left side is in K. Right. Right. So we assume they're right. We assumed that their intersection was 1, and we considered a commutator and proved that it's in this intersection. Okay. So this is in K. This is in H, so therefore this is in H, and this is in K. Okay, so this is in both H and K, and since their intersection is equal, and since their intersection is equal to 1, the commutator is equal to 1, which means that they commute. Okay, yes. Conversely, suppose F is an isomorphism. Now I'm confused by this last sentence. One may verify the conditions listed in the isomorphic group H times K instead of in G. What does that mean? Suppose it's an isomorphism, then It has to be injective, so sure on this. It has to be surjective, so yes. And H and K, oh, he's saying you can prove. I'm going to put I kind of understand, but kind of don't. I'm going to highlight this in glowy green, because this is a suspicious looking argument. I think what he's saying is that you invert the isomorphism. So you think about it from G to H times K. Okay, right, so if we go up here to this graph, so we go from G into G times G, G prime into G times G. If instead you go from here over, take the projections downward, and you know what I mean. Kind of invert the way that you're thinking about this. One may verify the conditions okay, suppose it's an isomorphism. Then the intersection in H times K I'm a little bit confused about this argument. I'm going to put a question mark next to this, and I'm going to move on. That's going to bug me, but I'm going to have to come back and think about this. I'm going to put a question mark here. I don't quite get this. Because I think I get the idea, which is if you're assuming it's an isomorphism, then it's trivial to verify that H and K intersect K are equal to 1. That's certainly true from the fact that it's a product group. H times K is equal to G. See, I'm a little bit... okay. Yeah, we're gonna definitely... I'll put a green star next to this for go iron this out on my own. Okay? For go iron this out on my own. Green means go iron it out on my own. Okay. There are two isomorphism classes of groups of order 4. The class, let me save. The cyclic group C4 of order 4 and the class of the Klein 4 group, which is isomorphic to the product C2 times C2 of two groups of order 2. Let G be a group of order 4. My brain is still hurting from that last argument. I'm a little bit... Okay, let me try it again. Okay? So H and K are normal subgroups of H times K. Totally agree. This one is confusing me. Everything in H... Yeah, so this sentence needs to be ironed out. I think I understand the logic. This point is tripping me up. This H times K is equal to G. This is tripping me up. I don't see how it's not obvious to me that is something you can conclude. Anyway. There are two isomorphism classes of groups of order 4, the class of the cyclic group C4 of order 4 and the class of the Klein 4 group, which is C2 times C2. Let G be a group of order 4, the order of any element of that's Lagrange's theorem, so there are two cases to consider. Oh my god, how much longer do we have? Okay, this is it. Okay. Let G be a group of order 4. Okay. So G contains an element of order 4, then G is the cyclic group of order 4. Okay. Every element of G except the identity has order 2, because is it true that the identity is the only element with order 1? Yeah, that's true. Because if there's another element that is, yeah, by definition, if an element has order 1, it's equal to the identity. So every other element, there's only one other divisor of 4, which is 2. Okay, so in this case, x is equal to x inverse for every element of G. Let x and y be two elements of G. X is equal to x inverse for every element x of G. Right, because it's of order 2. Let x and y be two elements of G. Then xy is order 2. Let x and y be two elements of G. God, my brain is just melted from that last argument. This isn't complicated. Okay. Okay, let x and y be two elements of G, then xy is order 2, so xy... x inverse, y inverse. Oh, because x is equal to x inverse is xy, which is 1. This shows that, right, because the commutator is equal to 1, so that since these are arbitrary elements, G is abelian, so every subgroup is normal. We choose distinct elements x and y and G, and we let H and K be the cyclic subgroups of order 2 that they generate. Okay, wait a minute. Distinct elements x and y that are not the identity. Because, okay. And H and K be the cyclic subgroups of order 2 that they generate. God, I hate just remembering cringe moments from my past. Thanks, brain. What? Why is it just like bringing that up? Why? There's that meme of my brain with happy memories, and it's like fingers in the sand, and then cringe memories. Just for some reason deciding, okay, now, okay. G is isomorphic to the product group H times K. Sure. Okay. Yeah, that's correct. I understand this argument. Yeah. Okay. I'm spent. That last sentence is tripping me up so much. Maybe that's what the thumbnail should be about, is this sentence. Alright, if I bottleneck on the thumbnail, I'll never release this video, so maybe I won't do the thumbnail. Okay. So this is the core idea. This is the main theorem of this section, is this 211.4. Okay, and let me switch to, this is the main theorem, okay? Main theorem. And I bet it'll be referred to a lot. Okay, and so what's the core idea about maybe we start with up here, okay? G times G, we take these two projections and then we combine them, and then so we do H times K, and then we combine H and K with no, you can't do that. They both have to be subgroups of the original group. So can you always do a projection onto one of your subgroups? That's an interesting question. Can you always do a projection onto one of your subgroups? Trying to figure out how to make this a diagram. I think Dummett and Foote has I think Lang calls this like the butterfly theorem or something like that. Can't remember. Lang has weird names for things. Okay. So let's think about how to make this into a diagram. So like the core theorem is this, okay? And is there a canonical injection from any, if H is a, yeah, there's obviously a canonical injection. Okay, yes. Okay, so let's do the coloring first. Okay, we're going to definitely be making use of colors. I like the yellow and green. Okay. So H down here we have K. Okay. And then we're going to need to make these really big. This is H. This is K. I just noticed in the last one. Okay. And then way over here we have G. Let's call these, should we color code the maps? Okay, and then here we're going to have H times K. And then the real big question is, what is the relationship between these? Okay, And then we form this map. So into HK. I need to use more vertical space, don't I? Anyway, it's fine. Which HK, which is thought of as a subset of G, and then this will be fine. And then let me like outline this. And then the question is, what is the relationship between HK and G? But I will write that in. I'll write that in text. So we are in downloads. This is AA30. Okay, we're going to save this as AA31 thumb draw. This is in downloads. PNG. Okay, let's go over to GIMP. Okay, and Control Open. And let's just rescale it right in place. So it needs to be 1280 pixels wide. Okay, that's fine. Doesn't need to be perfect. Yeah, okay. And then a new one, which is, oh shit. Let me rescale it. Image rescale. No, 1280. God damn it. Let me look at my fucking undo tree. Okay. Image rescale. Okay, Artin, you can go get off my fucking desk. That was pretty good. That wasn't, the last one was one of those Eureka. This was 1280 scale. Okay, this is what I want. Yes. Okay, and then a new one, 1280 by 720. Why does it do that fucking stupid thing? Okay. Background color. This is going to be the beach background. Delete layer. Okay. Copy, paste. Okay. To new layer. This is going to be drawing. Let's just 1002. Okay, and then I'm just gonna, in the corner, put that this is AA32 and blow that up a bit. Bold. Doesn't doesn't need to be 118, can be 60, that's more than enough. It might even be too big. Okay, and then the question is, what is the relationship between HK and G? Let's get this to be the right size, and this should consume the whole thing. 1280. If GIMP's going to be dicking me around again, I'm not in the mood. Although I've got alcohol. GIMP, what did I just say about dicking me around? Okay, this AA32 might have to move. Yeah, that AA32 is definitely going to have to move. Bold. Nope. 69 point is nice, but this AA32 is dead. GIMP! What did I just say about dicking me around? Do we have to have this conversation every day? Okay, and this has to be in a different color now. GIMP! Knock it off. GIMP! For fuck's sake! What is your problem, you piece of shit application? Jesus Christ. Okay. You're going to go down here. How about this? We'll make you centered. And then that way it's like even. And we'll... Okay. There we go. GIMP. Enough. I'm not in the mood. And then should I just say abstract? Go. No, that's too much. GIMP. Why are you like this, GIMP? Nobody likes you. This is why people use Photoshop. Okay. These need to be bold and bigger. Bold and 110 point looked about right. Okay. This needs to be glowy green. K needs to be the bright blue. And this needs to be the that's really the central question. Do I need this Q thing? That's stupid. Obviously it's a question. Okay, and this is Downloads. This is AA32 thumb. Yeah, this is good. Okay. Alright, I guess I need to stop the video, encode it, and upload it. Alright, I will see you in the next one. I'm satisfied. This isn't a great graphic. It's not as good as the last one. The last one I was like, oh! But this one I will live with. Okay. I probably will think of a better one later, but this is good enough. Anyway, thank you. Bye. Oh my god, I need to mention that it's Artin 2.11. For fuck's sake, obviously. Artin 2.11. Yeah. Yes. Yes! For fuck's sake, again, I swear to God. Stop.